Welcome back. And now we carry on with the Shattering coefficient estimation. But we are going to use a package, an R package that I wrote it. I've been working to put it available on the CRAN platform. And if it gets like shared by the CRAN platform, of course it's going to be available for many more people. And this is the paper, of course, I mentioned before, which I wrote to come up with an efficient way of estimating the Shattering coefficient function. Okay, it's available in the archive. And here is the code I wrote. First of all, I'm going to install this code. If you guys have R, you can just perform the installation like this. And then you type your password, because I'm using sudo here, and it's going to install the package for me. And just I start showing, okay, how to install. And after installing, of course, I can open R, I can load my package, and my package comes with I think it's run test with a simple example, which is interesting already to show some results. Here, I'm just going to run like its basic version for you and see the results like this. Okay, just to start. This is the sample that was produced by this example. Okay. It's got like, I don't remember, I think it's like 200 elements, okay? So like 100 red points and 100 black points. This is the number of homogeneous regions. As you guys may notice here, our n is varying from 1 to 200, and the number of homogeneous regions is almost like 25, 27 over here. So it's somehow reducing. If I come up with a linear approximation here, I can verify how many homogeneous, how is like my homogeneous, the trend or the slope of this reduction in terms of homogeneous regions. And this is the Shattering coefficient being estimated. In red, the worst case, the worst Shattering coefficient, and in black, the best. Actually, Harpeld and Jones, they proved two bounds. The worst case using a big O and the big omega, providing the lower case, the lower bound for our Shattering coefficient function. In here, I'm just plotting both, okay? So you guys can just play with this, passing like different means over here. Like if I change the means here, it's going to change the mean for the bidimensional Gaussians over here. And if I just provide a different n, it's going to change, of course, the sample size. If I provide like 500, it's going to be 500 elements in the negative and 500 in the positive class. Of course, black and red here, just to illustrate the whole process, okay? And you guys can just observe the outputs over here of the algorithm. It's running, it's estimating the number of hyperplanes we are going to have according to a different sample size. Okay? And in addition to this estimation of the number of hyperplanes, we also see over here an estimation for the Shattering coefficient. So it's going to build up the Shattering coefficient based on this estimation. Now I'm going to open the code and show you guys the code. It's going to be there running. It's going to take more time because it's just like 500. Of course, this turns out to be 1000 points in my space. But let's see. I will just uncompress this file. Let's see. This package is going to uncompress it. Oh, sorry. Like T Z. Okay. Those are the files we have inside this this package. I prefer to uncompress those like this so you guys can see. Okay. Of course, the most important files are inside this directory R. Inside it, you guys can find the function to compress the space. This is the function responsible for using the equivalence relations to find homogeneous regions in my space. Okay? This is the function that right after runs to find the number of hyperplanes necessary to shatter a given space based on the work by Haar and Peld. And this one is like the one that takes advantage of all those codes that I mentioned before, those three, to come up with the shattering estimation. Okay. This is the example I ran with you guys, and this is the function connecting all pieces together. I will go for the test so you guys can better understand what's happening. As you might see, I'm just creating a sample, a data sample over here with negatives and positive elements, or elements belonging to class 1 and class 2. It doesn't matter the class here, it's just a way of building up an example. Here I separate the input space, which has 2 dimensions, from the classes that are in the 3rd dimension. I plot the whole data set, and then I run this estimate number hyperplanes. This is the function that provides the number of hyperplanes necessary to shatter a given sample. So this is, of course, very, very devoted to understand a particular data sample, a real-world data sample, and not just some abstract sample, okay? This is going to bring a list as a result. One of those elements is this one called estimation. This is the estimation in terms of the number of hyperplanes. Then I call this function estimate shattering, which provides the shattering estimation for us. And then I plot those results. I'm going to show you guys this estimate number hyperplanes, which is just like the most important to show now. Estimate number hyperplanes. This function receives the parameters. The parameters are, just to show you, this is interesting if you want to test it. Input space, output space, or labels, right? Classes. The length. This length is like the number of assessments, or the number of, let's say, this is quite related to the sampling rate. This is related to how many different sizes for my sample that I want to assess. If I use like 20, I will start with a given number of examples, and I go up to its maximum number. Just using like gaps or skipping some sizes. This is the quantile. The quantile is like, I'm not going to use the whole data set, but just like 5% of the data set, and those 5 will be the elements, the more difficult elements to separate. So if I have like a bunch of positives and negative elements with some class mixing, those 5% will be selected from the class mixing region of my space. If I use like 50%, it's going to be 50%. If I decide to use 1, it's going to be the whole space, even the regions whose class overlapping is not, whose overlap is not happening, okay? This is just an epsilon to make like some small correction I'm going to show you guys. Over there, we've got the code. It's a quite simple code. It's going to build up the equivalence relations as I mentioned in previous video. This equivalence relation function is going to build up some radius, some open balls centered at each point I have in the space and trying to connect that point to points belonging to the same class. If it doesn't belong to the same class, it's not going to connect those points, okay? This one is going to compress the space. By compress, I mean, if I can connect 2 points, I will represent those 2 as a single one, as a single point. If I can connect like 50 points, I will represent all 50 as a single point in my space. So this is a way of compressing the homogeneous regions. Over here, I'm just computing the lower bound and the upper bound of the number of hyperplanes according to the study of Harpeld and Jones, as I mentioned before in the other video, okay? And of course, as I referenced in this paper, Harpeld and Jones over here, and of course, if you open up the PDF file, you're gonna see it. It's still running over there. And then I just bring all that together in the matrix, just to save up and show the results later. As you guys, I just suggest you guys to take a look at this function, equivalence relation, compress space. I'm just going to open both equivalence relation and compress space. So equivalence relation is going to create those open balls with a given radius. You can see that I will come up with those radius based on the quantiles that someone provided. And the quantile, of course, will just make sure that I select the worst case points, which are, of course, involved in class overlappings, to assess the number of homogeneous regions we've got in the space, okay? In the whole space. I'm using sparse vectors and sparse matrices just to make it run faster. Otherwise, it's going to take like forever to run this. Guys, take a look at this code if you are interested in understanding the details. And the compress space is over here. It is a function that runs like iteratively, just reducing the space, reducing up to a limit which does not allow a further reduction, a further space compression. That compression reduction is in terms of homogeneous regions. Remember, if I can connect regions, I just proceed with that connection. And again, using sparse vectors over there, okay? All that together is inside this, as I showed you guys. And there is another function, just to go back over here, number. Oh yeah, equivalence relation, compress space. And if I go back to my run test, just to show you my run test, after estimating the number of hyperplanes, I use this function, estimate shattering. And the function estimate shattering is over here. Estimate shattering. Yeah, it's over there. It's going to compute, basically, it's going to compute those binomials. This function, this R function, choose, computes binomials. So if you guys come up like with, oh, it's still running. As you guys can notice, it takes time, but no problem. Choose 5, like a combination, using like 1 element or 2 elements or 3 elements or 4 elements or 5 elements. Of course, it's going to work like this, okay? So that's how I solved the binomials over here. And this is basically a 4 summing up and employing that multiplication to come up with the total result for our shattering coefficients. Okay, that's all. And I just suggest you guys take a look at this code and compute some shattering coefficients so you guys can see. At the end, oh, you know what? I think I'll do something like this. I don't remember how many. Let's see over here. When I ran our last test, oh, I was using like a very large quantile, like quantile 50% of points in my space, even points that were not involved in the mixed region, in the overlapping region were considered. So I'm going to use like a different quantile percentage, could be like just 10%. Yeah, let's see the result. I think it's going to run like faster so we can check it out, the results, and see what's happening. Yeah, if it takes too long, yeah, it's taking a little long, 5%. Let's see, just to make it faster. Yeah, it's almost done. So we're going to see, okay, here we have the data sample. The second plot, we're going to have the reduced space, or we can also refer to this second chart as the number of homogeneous regions we have as the sample size increases. Taking time. Yeah, I know it's slow, but anyway, it's computing like the analytical formulation, so it takes time. Yeah, no problem. Let's wait like a little more. Doesn't run, I can just reduce the space, maybe use less than 500. Yeah, let's run for less, 250. I'm not interested in taking like that much. As you might notice, here is the data sample. There is some mixing. Number of regions, homogeneous regions. Homogeneous, remember, by homogeneous I mean under the same class label. Number of examples in total, doesn't matter the class label. So it goes up to 500 because I'm creating 250 elements per class. Here we have the shattering for the worst case, shattering for the best case, as the sample size increases. Okay. Here, something to see after seeing all the outputs, we can see the this is the slope of this curve over here. Of this actually a regression that was considered on top of this curve provided this as a result. What this means is that basically 5%, almost 5, right? 4.98% of the elements are somehow mixed. And of course, I'll have problems, difficulties in classifying those. If I have difficulties in classifying those, at least I can use this algorithm as well to understand how many are really separated from each other. So I can say that any algorithm built on top of this providing an accuracy around 95% is a good algorithm. Okay? And here we have the number of hyperplanes being estimated, like for 2 points, reducing from 10 points to 2. I have like this big omega, which is like the lower bound, okay, and the upper bound. Of course, a negative number means basically nothing, but no problem. This is going to be like 2 powered to this number to define the number of hyperplanes we need, okay? So it's not going to be negative, it's going to be something like this, okay? When we round, when we use the ceiling, sorry, it's going to be a single hyperplane for this scenario. That's what this number means, okay? And the same happens for this sample size, this up to the last sample size, which is 500. That parameter length, in this case, I set length as 5. 5 means I will start with a given sample size and increase in steps up to 500, just having 5 scenarios being analyzed. If I decide to use like 20, it's going to use, of course, 20 steps over here. And this is the lower bound and the upper bound shatterings being computed. Of course, I can make a regression for this function and a regression for that, as we did together in GNU plot, to see how they behave. If I use, like, as I mentioned before, if I use something like length equals 20, you see that we have like many results, many more. So the number of hyperplanes estimation in terms of the number of hyperplanes is going to start with this sample with 10 elements, then 35, then 61, up to 500, analyzing 20 different scenarios. And these are the shattering coefficients. Of course, the resolution is just better. Yeah, just more elegant, I'd say so. Of course, we can analyze like more points in my space like this. But if I analyze more points in my space, it's going to take more time. If you guys can wait, no problem. Of course, I can also reduce my sample size and perform the same analysis, just reducing my sample size. Oh, this is the case probably when the length is not enough. Yeah, length probably is too great in comparison to my sample size. I should change it. Yeah, this is another scenario. You guys can see this here. We analyze 20 scenarios, increasing in 10 every time our sample size. And of course, here we have the original space, reduced space, original space, reduced space, and so on. Okay. There is like some bumps over here that makes this happen. And here we have the shattering coefficient over there. This is due to those bumps, and those bumps are especially because my sample size is not too big and my quantile is not considering as many points as it should. If I consider like all points, that's the case when you use 1 here. Of course, the resolution is going to be better. It's going to be improved. Okay, so it's running. Yeah, much better. Yeah. So of course here we are considering all points. This is the curve that shows me how many homogeneous regions we have in terms of the number of samples, and here the shattering coefficients. Of course, I can come up with a function approximation, a regression over here for the worst case and the best case, and plug both in the generalization bound and analyze our scenario, our problem, our data space. Okay, guys, see you in the next video.